You've probably seen the photo. Earthrise is one of the most significant photographs in the history of human civilization, certainly the most iconic in space exploration. Taken by astronaut William Anders during the Apollo 8 mission, the first crewed mission to orbit the moon on December 24th, 1968, this photograph captured the imagination of the world. The image itself is remarkably simple, yet its impact was immediate and profound. It shows the Earth rising above the lunar horizon, with our planet's blue and white colors standing out against the stark, barren surface of the moon, all surrounded by the black vacuum of space. Our little blue dot floating in the vastness of the cosmos. Fast forward to today, and we have thousands of satellites in orbit looking back at us. These satellites perform a variety of critical tasks, from positioning, navigation, and timing to telecommunications. But above all else, they continue the legacy of Earthrise by keeping an eye on our planet. Satellites today are active participants in managing and understanding our planet, monitoring weather, ocean currents, and topographical changes. They track the health of coral reefs. They play crucial roles in agriculture by predicting crop yields, in urban development by aiding city planners, and in disaster response by providing real-time data on natural catastrophes. They also contribute to conservation efforts by tracking animal migrations and monitoring endangered species. Essentially, they take selfies of Earth. Next time you open up Google Earth or a similar maps application, you're seeing the result of this advanced photographic technology. But unlike the modified Hasselblad camera used by Anders, today's satellites are far more sophisticated, and their power requirements are much more complex. The first lunar module was famously less powerful than the smartphones we carry in our pockets. When our phones run out of battery, we simply plug them into the wall and wait for recharge. Satellites, however, face a different challenge entirely. Space power design is a daunting task. Here on Earth, we can dispatch a service technician to fix issues as they arise. Up there, satellites are on their own. This is where advanced power management and delivery systems come into play, and the need for radiation-tolerant components qualified for space applications becomes critical. These systems must capture energy from solar panels and distribute it efficiently to each function within the spacecraft, often at ever-increasing voltages. There's no room for error. The components need to be installed and designed right the first time. Satellites have evolved from simple observational tools to complex systems that provide critical data for a wide range of applications, all aimed at making our lives better and our planet more sustainable. As we continue to push the boundaries of what these incredible machines can do, the importance of reliable and efficient power management systems cannot be overstated. How can microchip technology power and drive the evolution of satellite technology? Let's go beyond the microchip and hear a story of empowering innovation to enhance the human experience. Our guest today is Oscar Mancia. Oscar is Senior Applications Manager at Microchip Technology, working out of the Discrete Products Group. He joins us today from his office in Lawrence, Massachusetts. Welcome, Oscar. Thanks for joining us on Beyond the Microchip.
Hey, Dana. Happy to be here.
In the intro, we briefly talked about space technology, specifically satellites, and the evolution of space power management. What inspired this talk was that famous Earthrise photo and what has been dubbed as the greatest selfie ever taken. Let's talk about that.
Yeah, let's do it. I mean, for me, it's just everything that must happen in parallel to get to that point, and then from there, what transpired after in terms of the evolution of technology and the things that we currently do now from space and how it impacts our daily lives. Right? So if you basically take that image and just break it down into two fundamental halves. One is the photography portion of it, right? The selfie portion of it. And that itself has its own fascinating history. And then you talk about space exploration and the technology used in space exploration. And then what everything had to happen, or everything that has happened, for them to merge at that single point in time to take that greatest selfie ever taken, right?
Yeah.
Just a little bit about the selfie history, I would say, right? I mean, there's a lot of evolution and a lot of technology that has happened just looking at the selfie, right? Even back in the 1800s when it was the first self-portrait, to the 1900s when there was like a Kodak Brown, which is basically a cardboard box. Basically, people used that to take pictures. And then as you moved into the 20th century, you got in the 50s and 60s the Polaroid, right? Instant photography, easier for people to take and immediately view their self portraits. And then you come into the digital revolution of the 90s with the first digital camera. Really revolutionized the photography, right? Eliminating the
Hmm.
need for film, allowing for instant review and deletion of images. And then after that, you have the rise of the smartphones, right? A smartphone with the camera, you could take your picture, you could view it, internet connectivity, you could send it, you could post it, etc. Right? So that in itself is fascinating. And then you have the space exploration portion.
Hmm.
And at that time, it was advanced technology for its time, right? As you mentioned earlier, it was the first manned mission, Apollo 8 mission. And it
Hmm.
was one of the first times that the Saturn V rocket was used, right? So the Saturn V rockets, which that in itself is also an immense technological task, right? I mean, the Saturn V rocket, 363 feet tall. That's taller than the Statue of Liberty, weighs 6.2 million pounds, and it took about 6 years to develop. So from 1961 to 1967, it was in development. It was used in a couple missions in 67, and then, of course, in the Apollo 8 mission in 1968. And then you add to that the selfie, and you have that picture that we're talking about. And then from there, what transpired is, I would say, a self awakening of the people on Earth, right?
Hmm.
Um, for the first time, I think you could sense, that global unity, that we're all in it together, right? And then it spawned a lot of different, I would say, perspectives. And the first one, of course, was that environmental awareness, the ability for us to monitor ourselves, what's happening on the Earth, with the Earth observation satellites.
But we're not just we're not just up there taking pictures, right? So the idea of looking back at ourselves in that profound moment that you're talking about, that
Mhm.
kind of came from this need to now view the Earth as, trying to think of how I want to say this. The whole idea of Earthrise was that it now made us think to ourselves, we should be looking at ourselves. It was kind of that looking in the mirror moment, right?
Correct. Yes, I think that's the awakening that people, uh, received at that time. Right. It's for the first time from a wider perspective. I think you're looking at yourself in the mirror, and you're seeing what you're doing in general, right, to the earth and this beautiful place we call home. And then that affects a lot of people on how they move forward again with the global unity and then the evolution of, okay, how do we monitor ourselves? What can we use this technology to improve our daily lives? And, how does that impact on a day to day basis now when, you know, we're out there just driving to work or picking up our kids from school without really realizing, all that has happened the last, 60, 80 years, for us to be able to do a lot of things that we do at such a speed as quickly at such a high speed, right? And understand ourselves in terms of, these are our ability to view ourselves and then do things that improve our daily lives.
Yeah. So it's one thing to send it up there with an antenna or with a beacon or a set of sensors that we can handle for GPS or to give us an opportunity to do telecommunications back and forth. We sent a camera up there specifically with the job of looking back at us, which is where we get that idea of the selfie, of that moment where we want to see ourselves. But it also allows for productivity, allows for safety, it allows for research and development and understanding of the planet itself. And that was really,
Exactly.
really a huge moment in not just climbing up a hillside and looking down on the city that we live in, but now we can actively predict, right?
Correct. Yeah, exactly. So that opened the door for a lot of technologies in terms of, Earth observation satellites, right? That's number one, right? How do you improve or how do you go beyond just the camera? What else can we add to the satellites and what kind of sensors to go and monitor the health of the Earth, for example, to go look at climate change or deforestation. Uh, Also, we could get help on crop monitoring, figuring out the best soil moisture point in on the earth to improve agriculture that will feed us, right? It helps us with urban planning and development. And then, of course, it always helps us with security defense,
Hmm.
surveillance, military surveillance and reconnaissance, etc. And then also with disaster management, right? So early systems, early warning systems to see, where, some, uh, bad weather is coming, a hurricane or a typhoon, etc. We could definitely, monitor that more closely and warn people ahead of time.
And so in the early days, they took pictures, then sent them back, and then we processed those pictures here. But now we're actually going to start having maybe some logic or processing in the camera vision of the machine vision itself.
Correct. So if you look at a typical satellite system,
Yeah.
you know the down the downward link. So the downlink has always been the bottleneck, right? We could take pictures and we could take image sensors, input from sensors, but all that information needs to come back down to ground base so we could do the processing or look at the results and then react from the results. um, but that's a lot of data coming down.
Hmm.
So
Yeah.
what's going on is they want to eliminate the bottleneck and only send the useful information. We don't want 10 million pictures as an example of the forest. We only want that picture that shows us where the fire is occurring so we could pinpoint its exact location, react accordingly and swiftly, and eliminate that threat. Right? So, what does that mean? That basically means the increase of onboard processing in satellites. So the satellite itself now has to have the ability to do a lot of computing where it's taking these images and then doing some kind of processing to detect that there is a fire situation here in this location or in this forest, and then just send that portion of the useful information back down to earth. And that there requires a lot of data processing, right? um, it requires a lot of more digital components, and that's, I would say, one of the early uses for artificial intelligence in space is actually image and pattern recognition. Can the computer in the satellite in space be able to detect something based on its processing capability, and then just send us back the useful information to go for us to go react to it?
So we're getting away from a static sensor relay or a static picture taker. We're now getting to a kind of a, is it fair to say, a thinking machine up in space?
Correct, and it's both on both ends of the technology, I would say, right? It's both on the picture capture portion of it, right? That
Hmm.
technology itself has evolved, right?
Right.
Something like what they call a SAR now, right, which is a synthetic aperture radar, and that one, and that it's like a picture. It uses the motion of the radar antenna on a target region to simulate a much larger antenna. That's why it's called synthetic apertures. And then what happens is, as the satellite moves along its orbit, the radar continuously transmits pulses of microwave energy towards the ground. The radar receives the backscatter signals from the surface feature, and then those signals contain information about distance, the relative motion of the reflected objects, and you're able to then use that information to basically create a picture of what you're looking at. And one of the good things about that is that you don't get disturbances because there is a cloud or there's some other kind of objects that are typically in the sky, right? And you can't take a picture. You take a picture of a cloud and then you can't see what's underneath it. This
Right.
type of this type of system basically allows you to go through that and capture very, very, I would say, high resolution images of what's at the surface level. And in some cases, depending on how you set the frequency and the phase delays, you could actually go below ground and just capture what you really need, or even below the surface of the water as well.
Wow.
So that evolution has happened not just from a still image, but the actual how you take the picture has really improved over the last couple of years to eliminate some of the barriers that are always there, right? Which is typically the clouds and things like that.
That's kind of allowing us to map the ocean floor, right?
Correct, exactly.
So
So,
we
so
you have the cloud as a problem, but then that actually is one of the applications, right? Is tracking and predicting weather analytics. Do you think that this technology will allow us to be able to better accurately predict weather patterns?
I believe it would help us to detect uh, cat- catastrophic weather situations more quickly. Whether it would allow us to predict it, um, I don't believe so. I believe
Okay.
that it would just help us detect, and then we could react faster, and ensure that the safety of a lot of people occur.
Okay. So the original Earthrise picture was taken with a modified camera, and I think it was the Hasselblad. I want to say,
That
and
is
my
correct.
understand
Yes.
and my understanding is that took 3 volt nickel cadmium batteries. Clearly, we're well beyond 2 NiCad batteries, right? Somebody's got to power all this. So, what kind of
No,
technology are we looking at modern satellites?
no, you're correct about that, right? I mean, again, you have the power, the actual, let's say, the actual camera. In this case, let's talk about back to the SAR, the synthetic aperture radar, which has a lot of components. It's very power hungry, more so than a couple cadmium batteries. But then,
Hmm.
if you want to add to that the processing, right? In order to enable data processing, you're going to need components such as the microprocessors, right? Microcontrollers, FPGAs. You may have an application specific integrated circuit, ASIC, that
Hmm.
does just the data processing. Everybody now talks about for artificial intelligence, right? NVIDIA with the graphic processor units are also one of the main staples in doing a lot of the processing. And it's just not the processor, then it's the peripheral digital circuits around it, right? So you might need memory, non-volatile memory, DRAM. You're going to need communication chips. How do you send that data from one part of the satellite to the transmit portion of the satellite, and then how do you send through RF signals back down to Earth? And that also requires more different kinds of power as well. So yes, it goes beyond um, just the actual digital circuits that enable this technology, but the backbone of what really makes this work and makes this happen is the power management and distribution systems.
Hmm.
And
Yeah,
they have to
PMET.
be yeah, exactly, and they have to be very efficient, right? Because you're only relying on solar panels, solar power at this point, and in some cases you're going to be relying on the battery when the satellite is no longer facing the sun, or away from the sun.
Right. And we're requiring more and more voltage and more thresholds for power demand, right, as the technology gets more complex.
That is correct. If you look at the history of, for example, FPGA, right?
Yeah.
You mentioned earlier, the battery took about 3.3 volts, and maybe it could be supplied out of a couple cadmium batteries.
Yeah.
Now, the microprocessors and FPGAs, the modern, are going down in voltage. Where historically it could have been 3.3, then it went down to like 2.5, then it went down to like 1.2. Now you're looking at sub 1 volt, 800 millivolts for some of the modern FPGAs that work in, like the 10 nanometer technology scale, even
Hmm.
600 millivolts for some of the smaller technology scales as well. But the voltage has been going down, but the power has been going up, which means that the current consumption of these devices has increased significantly. So if you're talking, for example, 1 volt, and the power consumption of FPGA could be maybe 80 watts to 150 watts, that's 80 amps to 150 amps of current that needs to get delivered by the PMAT system that is provided power or energy from a solar panel.
Hmm.
So there has to be a lot of efficiencies, smart designs, picking the right components, ensuring you're doing it reliably. As you said, you can't just plug it in back into your outlet, right? It needs to work. So the components that you pick need to be reliable and be able to operate in space. So you got issues with the radiation
Yeah.
performance,
Yeah. Why don't we talk
heavy
about that?
ions. Yeah. So that's one key thing, right? Compared to the CPUs in here, which are powered by just regular transistors, I would say, or regular power management ICs. The ones in space need to worry about two different things. One is the ionizing dose radiation, which is basically accumulation of charge in the device. And in the MOSFET, for example, you accumulate charge on the device. And what sometimes happens is that it accumulates so much charge that you really can't turn off the device. So it no longer behaves like it's supposed to. You can't control it. You can't turn it on. You can't turn it off. It's just always on. And that's due to what they call total ionizing dose radiation. That's one effect that it could have on the MOSFET. There's a lot of different effects that it could have on different type of integrated circuits. But if we focus just on the MOSFET for simplicity reasons, that's one thing that could happen. And then you're also worried about cosmic rays, heavy ion energies. These are, I would say, single particles that would hit your electronics. And what that does is, as it transverses the electronics, it basically emits a lot of energy into your device. And what could happen is that it may cause an increase of energy so high that it might damage your device, or it might cause it to behave abnormally for a couple seconds while the device recovers, right? So in the MOSFET, for example, again, going to a simple transistor with what's basically used as a switch, if a heavy ion basically transverses the sensitive region of the device through the gate, we have what we call single event gate rupture. And what that happens is basically the gate gets destroyed. And again, you can't control the device at all. And this is due to the heavy ion going through the MOSFET device and connecting or shorting the low voltage gate to the high voltage drain. And the gates can only support, let's say, 20 volts, and you might have, 100 volts on the drain. And the heavy ion basically shorts those two points together, and now you blow up or have destructive events on your gates. So those are two different types of radiation that all electronics needs to be worried about when you're in space. The ionizing dose radiation, which is the accumulation of charge within the circuits or within the electronics, and then heavy ion particle, I would say, radiation, right? And those are called single event effects because usually those occur due to a single particle, and it hits the device in one single location, and then that might cause destruction or just an anomaly in the way that the device is behaving, and then it may recover.
When we talked to Eli and Bill about some kind of generic space applications of the technology, they talked about bit flipping and latch up. Does that apply to power components as well?
I would say latch up does. So bit flipping is more to like a digital element, like a memory element, where you would, had it programmed in there a 0, and then all of a sudden you get a heavy ion strike, and let's say it's a low energy one, where it was just enough energy to turn it from a 0 to a 1 or a 1 to a 0. So you bit flip device,
right.
And of course that could have detrimental response right to the whole system. That might cause the whole system shut down, especially if it's a memory device that you were using to boot your FPGA. So it held the program that you were going to install into your FPGA so it could do its processing. If that one bit changes, it might change the whole program and make your FPGA inoperable, just as an example. In latch up, I would say that also applies. That probably applies more so than the transistor into the MOSFET than the bit flip does, right? Because that's more for digital ones and zeros. So the way that latch up occurs in a lot of cases for the MOSFET is that it has a parasitic NPN transistor, and what happens is basically this heavy ion gives it enough energy such that the transistor turns on. And then when the transistor turns on, you have a lot of current flowing from the base to the emitter, and you also have some feedback back to the you have a lot of current coming from the collector to the emitter, and then some feedback current back to the base, which as you increase your base current, then you increase your collector emitter current. And this basically feedback that it has increases current indefinitely until you destroy the device and the part can no longer handle it. And then you're in a latch up situation or a destructive latch up situation. So, yes, latch up applies more to power devices, I would say, than a bit flip would do to for a power device. That wouldn't apply as much.
I know you can build in redundancies for bit flipping. Can you build in redundancies for power?
That's very hard to do.
Okay.
So I think a lot of redundancy, it works well when there are digital circuits, right? When you are just going for 1-0-1-0, you could actually have three parallel paths, and at the end of that, you could have a voter. And if two of the paths match, then that's the one you pass through. So if something bit flips, it flip, or you have what how we call this a single event transient is usually what they call it, a transient event due to a heavy ion. It's very hard to have triple redundancy because it's analog function, so you don't have just 1 or 0 to do a majority voter type of results.
Right.
What they do implement in a lot of devices is like filtering. So maybe they put a big capacitor, as an example, on the gate driver to the MOSFET. So in case there was a hiccup on the driver due to a heavy ion, the capacitor would not change the state of it immediately. So one things like that could be done in analog signals. A lot of filtering is usually done.
And that's what leads to the need for radiation hard and rad tolerant, right?
Correct. I mean, you can't get away from power, and power at the moment is all analog. Again, if we go back to the FPGA example where they may need 800 millivolts, and your power solution is an analog solution, typically, if it deviates above the plus and minus 5% of that window of 800 millivolts, in many cases you're going to either destroy the FPGA or just not have enough voltage to continue processing. So that's why it's very key for a lot of the analog signals, including the power systems, for it to ensure that you have the most reliable components that you have in space, which includes radiation hardened to TID as well as single event effects in the heavy ion environment.
So which devices among Microchip's catalog would apply to what we've been talking about today?
So for the power management technology, I would say that Microchip offers a lot of different devices. The first one, of course, would be our newly released radiation hardened MOSFET technology. We call it the M6 technology. These power MOSFETs range from 100 volts to 250 volts. They are offered to a Jan S, which is the highest level of screening available to any component, and sold to MilPerf 19500 /E, which is the equivalent to a data sheet, but that's basically governed by the DLA, which is a government agency. So that's our MOSFETs. Again, the MOSFETs, and why I'm talking so much about MOSFETs, because MOSFETs are really the muscle of a power management distribution system. They take the voltage that you need, they convert it to a lower voltage, different kind of current levels to really get distributed throughout the whole power system, right? So, they have to be the strongest parts of the complete system. And for them to be reliable, radiation tolerance, our MOSFETs are rated to 100K rad. We have shown performance up to 500K rad. And then we are developing 300K rad versions of these devices for some of these, I would say, interplanetary missions, right? So if you want to take selfies of not just the Earth, but maybe the Jupiter, or Titan, the moon of Saturn, for example, you're going to need some high radiation capable devices. Our M6 technology for the MOSFETs are going to be rated up to 300K rad. Right now we have the 100K rad version. The 300K rad is following that, I would say, within the next 6 months.
Wow.
Yeah. So, and then they're all rated to a high level of energy. I would usually what they call the LET. So our devices are rated to 84 MeV. which is industry standard for the highest rated energy using gold ions. A lot of the devices available now are sometimes available to that level, but in many cases below that, like 60 MeV or below. So we have the most one of the highest, I would say, LET values available for a power transistor out there.
We're well placed for deeper orbit devices.
Correct. Yes, deep orbit, interplanetary missions, those type of things, like the James Webb Telescope, right? Things that are going back, beyond our just traditional geo orbit. Definitely, we're placed in prime position to be used in those applications and those missions.
So, suppose one of our listeners has a use case for this technology. Where could they go? Where would we send them?
I would say they could go to our Rad-Hard MOSFET landing page, which is basically just www.microchip /space, and then you'll see the Rad-Hard power solutions.
Okay.
And then we could also look at our space solutions brochure as well.
Great. We'll put those links in the show notes.
Yeah.
At this point in the show, we always want to ask about a prediction. Now, a prediction is not necessarily that we're going to leave you on the hook, but it's kind of an idea of, based on what you understand and based on what the trend lines are, do you have any predictions about the future of where space power may go, and what could some potential future applications be? You mentioned James Webb Space Telescope, obviously, but is there anything beyond that? What do you think is next?
No, I think for the power management distribution systems, the PMAD systems, I mean, they're always crucial for space vehicles and satellites. I would say what's next is basically, as we move towards establishing a sustainable presence outside of our world, right? We're talking about the Artemis project, right? Starting with the lunar gateway, but then we're also looking at habitation on the lunar surface. And in order for us to do that reliably and safely, we're going to need a very reliable, robust power management distribution system. So it's moving away, I would say, from what used to be the backbone of just a satellite to the backbone of our presence in these outer worlds, like the moon, and then also from there springboarding us to the to Mars, right? If we ever get there, to set a presence there,
right?
And those power systems there, they're being smart about it, right? They're looking at higher voltages as an example. This would increase efficiency. It would minimize this overall size as well as the of the power management system with higher voltage and higher switching frequency. So one of the things that they're looking at as an example here, just to compare, here on Earth, what is it, 50 or 60 hertz? 120, 120 volts, 240 volts, right? Depending on which part of the world you are.
Right.
On the lunar side, what they're looking at, it's either 1.5 kilovolts as the distribution, or 3 kV or 3000 volts AC. And then they're also looking at a higher frequency, right? 60 hertz here. They're looking closer to 1000 hertz there. So what does that mean? So from a frequency standpoint, typically as your frequency increases, your passive components could shrink down. So that means the transformers, the big transformers that you usually see, outside driving in your city or your neighborhood, could actually shrink much more. Because you're talking about
10 to 15 times the voltage of a standard residential application like a dryer or refrigerator, right?
Correct, exactly. And the same for the switching frequency, or the frequency that it's coming in at. Right, much higher frequency, 1000 hertz versus 60 hertz. So what does that mean from a power management standpoint? That means that we need to have devices that could support that higher voltage reliably in space. So we're moving to different technologies, or there's going to be a need to move to different technologies, and things like silicon carbide or GaN that could support the higher voltages and that could also support the higher switching frequencies as well.
That's great, Oscar. Any final thoughts?
No, for me, I would say it's exciting time for space applications and exploration. Um, just over the last 5 to 10 years, right, there has been that shift from government agencies leading the space missions to private
To the
industries.
private sector. Yeah.
Correct, taking over the space flight. They call that new space, right? And they're looking at not just satellites, right? Yes, there's a lot of LEO satellites now to due to SpaceX and different other companies out there putting up their satellites. But the future beyond that is what really fascinates me. They're looking at going to Mars, looking at landing on the asteroid, mining for minerals, precious metals in these different asteroids and bringing them back. They're also looking at, can we do manufacturing in space, right?
Right.
Things like that. So I think
Zero
it's
gravity. Yeah.
zero, right? Exactly. So they're what what goes after this initial wave of the Leo constellations is what really fascinates me. I think it's going to drive another revolution in terms of how do we merge the technologies here with the capabilities that we can in space. And then it's going to spark a lot of creativity to try to use both of them in space because, we have, I wouldn't say unlimited, but we have a lot of resources here to plug in and develop data centers for artificial intelligence that, are the size of a football field. We
Mm-hmm.
really can't do that easily in space. So, how do we still be able to get some of that technological advancements and capability into space reliably, safely, and ensure that everything works properly? I think that for me is what's very exciting for me.
All on our way to becoming an interplanetary species.
That's right.
Thanks, Oscar. This is really great. Appreciate you coming on the show.
Thank you. Thanks for having me. Appreciate it.
Oscar Mancia is Senior Applications Manager at Microchip Technology. He specializes in aerospace and defense applications. He joins us today from his office in Lawrence, Massachusetts. Thank you for venturing beyond the microchip with us. Join us next time as we continue to explore empowering innovation to enhance the human experience.